Hello students, I welcome you all in the initiative offered by TEQIP Faculties called as Let's Crack the Gate, and this is lecture number 12. In previous lectures we have seen that about the context free languages, and we have also seen that about the push down automata which is used as a machine to accept the context free languages. In push down automata we have gone through the deterministic push down automata and non-deterministic push down automata. We came across with the non-deterministic push down automata because there are some languages present, that is context free languages are there, for which we cannot able to design a push down automata, that is deterministic push down automata. So for such languages we have designed the non-deterministic push down automata. Okay, and in finite automata we have seen that finite automata we have seen that deterministic finite automata, non-deterministic finite automata, and epsilon finite automata, epsilon NFA. Okay, all these finite automatas are equal, means from NFA to DFA, DFA to NFA, NFA to epsilon NFA, epsilon NFA to NFA. So we can say that DFA to epsilon NFA and epsilon NFA to DFA conversion is possible. Whenever the conversion is possible, means we can say that all these three are accepting the same languages. But in terms of deterministic PDA and non-deterministic PDA, there is no such conversion is possible, because there are some languages which cannot be accepted by deterministic PDA, but that can be accepted by non-deterministic PDA. For such type of examples we have gone through yesterday only. We have seen 2-3 examples. For that examples, designing deterministic PDA is not at all possible, so we have designed a non-deterministic push down automata. Okay, so similarly in this lecture we will see some languages will be given to us, and we have to identify whether that language is deterministic CFL or CFL. We are using that CFL word when the language is non-deterministic language. Okay, and also we will see whether that language is a regular language. Okay, so one thing is about regular language is always true, that whenever the given language is finite, definitely that is a regular language, means for that particular language we can able to design a finite automata. Okay, so let's see one by one, and we will so here I am not going to solve, or I am not going to design a particular PDA or DFA, NFA. Okay, so we have already gone through that. Just I will check the logic. Based on our logic we will decide particularly this is a DFA, or means we can say that regular language, or deterministic context free language, or non-deterministic context free language. Because if we are able to solve using one stack, we can say that, oh, this is the context free language, otherwise that language should not be a context free language. Okay, so let's see the languages one by one. So first language says that language is a raised to power m plus n, b raised to power n, c raised to power m, where m comma n is greater than or equal to 1. So here greater than or equal to 1 is there, so language is not finite, so we cannot say that that is a regular language or not. For if language is finite, then definitely it is regular. If not finite, means it is a infinite, then we have to check whether there is any loop or there is any arithmetic progression. If that is present, then whether we are able to design a finite automata for that or not, we have to check that. But we have already seen this language, and for this language we have already seen that we are not able to design the finite automata. So particularly we can say that this language is not a regular language, Okay, next, here a raised to power m is there, a raised to power n is there, and here b raised to power n. So a raised to power n and b raised to power n should be compared, and a raised to power n and c raised to power m we can compare. Okay, So for whenever a comes, we will push into the stack. For m a's, I have pushed in the stack, pushed into the stack. Similarly for n, we will push that a's into the stack. Whenever b occurs, these n bn's will be compared, and these are popped by using this b. And finally, whenever c comes, by using c, this number of a's are popped. Okay, so for this we are able to design a deterministic PDA. So this is a DCFL. Okay, whenever the language is DCFL, it is a context free language. Okay, okay, so let's take another one. So in this also, this is not a regular language because we are not able to design a finite automata for this, because we need a memory for comparison. So a raised to m power m and b raised to power m should be compared. Okay, we can compare that. Similarly, b raised to power n, c raised to power n, we can compare. Okay, so whenever b comes, we will push that, sorry, whenever a comes, we will push that a's into the stack, and whenever b occurs, that is b raised to power m, we will pop that b's, pop that a's using this b. And once stack is containing z naught at the bottom of the stack, then again we will start pushing these n number of b's into the stack. Similarly, these n number of b's will be popped by using when c occurs. Okay, so by using stack, we are able to design a pdf for this. So we are able to design a deterministic pdf for this. So this language is a DCFL. So whenever the language is DCFL, it is a CFL language. Okay, so let's consider this third one, a raised power m, b raised power n, c raised power m plus n. Okay, तो इसको कैसे लिख सकते हैं हम? This should be written like c raised power n plus m. So c raised power n, c raised power m. So b raised power n and c raised power n we can compare, and similarly a raised power m and c raised power m we can compare. So whenever a occurs, we will push that a's into the stack, and whenever b occurs, again we will push that b's into stack. Whenever c started occur, okay, so by using these number of n's, we will pop these number of b's. Okay, so by using c raised to power n, we will pop b's. Similarly, the remainings are c raised to power m, so by using that c raised to power m, we will pop a's from the stack. Okay, so finally we can say that this is not a regular language because we need a stack, and this, for this language we are able to design a deterministic PDA. So this is the DCFL, and when language is DCFL, it is always CFL, but reverse is not true. Okay, we will see that how the reverse is not true. Okay, let's see the other languages. Similarly, for this language also, we can say that a raised power m is compared with b raised to power m, and c raised to power n is compared with d raised to power m. Means for a, we can push that a's into the stack. Whenever b occurs, we will pop the respective a's from the stack. Again, when top of the stack is z naught, again we will push these number of c's into stack, and by using these number of d's, we will, sorry, here push, and here we will do pop. Okay, so finally if that stack contains z naught, then we can say that the strings will be accepted by using PDA. So regular, this is not a regular language because we need a stack, and by using PDA, that is deterministic PDA, we are able to design, means we can able to design deterministic PDA for this language. So this is a DCFL, and whenever the language is DCFL, it is always CFL. Okay, now in this language, a raised to power m, b raised to power n, c raised to power m, d raised to power n. So m and n क्या है, is greater than or equal to 1. So language is infinite, and we are not able to design a finite automata for this language. So this is not a regular language. Similarly, this language I have given you as a homework in that particular class, and we have seen that we are not able to match these A's with these C's, because in between we are getting n number of B's, and if we will push this into the stack, okay, for removing these number of A's from the stack we need C's, but we are not getting immediately C's, we are getting B's, so we cannot compare these B's with C's, because top of the stack we are getting B, and when input comes we are coming with C, so we cannot make comparison between C and B, so this will not be a DCFL, because we are not able to design a deterministic PDA. Also we can say that this language will not be accepted, or we cannot design a NPDA for this, so this is not a CFL language. Okay, then next is A raised to power m, B raised to power n, C raised to power n, D raised to power m. So we can say that for this A we can compare with this B, this D, and these B's will be compared with this. So whenever A comes we will push that A's into stack, whenever B comes we will push that B's into stack, and whenever C occurs we will compare B with C, and we will start, for each C occurrence we will pop one B. Similarly, when these are having same power, so B will be popped out by using these number of C's, and whenever we are getting D, then top of the stack will become A, so we will start popping A's by using these D's. Okay, so this is not a regular language because we need a stack, and finite automata is not having memory, so this is not a regular language. But for this language we are able to design a deterministic PDA, so this is a deterministic context free language, and whenever the language is deterministic context free language, then it is always a CFL. Okay, let's see another ones. So next language is A to the power m, B to the power I, C to the power m, D to the power k. M comma I comma k is greater than or equal to 1. Here we need a comparison, so we need a stack, because A to the power m will be compared with C to the power m, so we need a stack. So we can say that designing finite automata for this language is not possible, so this is not a regular language. So now we can see that I and k are different, means I is not equal to k, so we don't need to compare this B and D. Okay, so only the thing is that should be greater than 1, and I and k are independent to each other, so we need not to compare that. But whatever the number of A's are in the language, that number of C's will occur in the language. Okay, so whenever A occurs I will push that A's into the stack. Okay, and these A's I have to compare with these C's, because whatever number of C's are there, that number of A's are there, the comparison between A and C is possible. And whenever I am getting B's, I will just read it, I will not do any operation in the stack, no operation. Okay, and whenever I am getting C, I will compare that C with respect to particular A, and I will start popping. Okay, and finally I am available with Z0. Whenever I will get the D, I will just read that D, means I will not do any operation, because I don't care about these D's. Okay, because we need not to compare it with anything. Okay, so for design we can able to design the deterministic PDA for this, so we can say that this is a DCFL language, and whenever the language is DCFL, that is always a CFL. In this also, the next example, A raised to power m and B raised to power n, and m is always greater than or equal to, sorry, greater than n, always greater than n, means a is a1 is there, means m is always greater than n. Okay, m. Okay, when double a is there, means there should be at least only one b, because it is always greater than m is greater than n. Okay, so this will be possible. Then whenever a is 4, b will not exceed 3. B will not exceed 3, because compulsory we need more number of a's. Similarly, if we will write, suppose there are 5 a's, then 1 b is possible, no problem for that. Okay, and but it will not exceed more than 4. Okay, so whenever such type of things will come, what we will do, we will able to design a deterministic PDF for this. So how we will check whether that a is more or not? So we will do one thing, we will push when a occurs into the stack, and whenever we will push that a's into the stack, and after getting b, we will start popping each a with each b, and suppose we will left with z0 and top of the stack is a. We are here after finishing all the b's, mean the transition is like epsilon a. We will keep that a as it is, and we will say that we will accepting such type of strings, because we always want m is greater than n. So we are able to design deterministic push down automata for this one. So this is not a regular language, because we need a comparison, and by using deterministic push down automata solving this is possible. So this is a DCFL language, and we can also say that this is a CFL. Okay, so again this is the language, the a raised to power n, b raised to power 2n. We have already gone through this example. For 1a, we will push two a's into the stack, and whenever b started occurring, we will compare each a with each b, and we will start popping. So this is not a regular language, because we need a stack, and this is this language will be accepted by creating deterministic PDA. So we can say that this is a DCFL language, and whenever the language is DCFL, it is always a CFL. Let's see more examples about this. So the next language is a to the power n, b to the power n square, where n is greater than or equal to 1. So whenever a occurs, we have to push for comparing b's, but in this case we are not getting a, means we cannot put this b's into the loop, because when we are writing the language, so a is, suppose n is equal to 1, so I will get a b as a minimum length string, but when a is equal to 2, I will get a and 2 to the power 2, that is b 4 times. When n is equal to 3, I will write triple a and 3 to the power 2 means 3 square, that is 9. So b will come 9. 4, 5, 6, 7, 8, 9. So initially when n is equal to 1, I am getting 1 1. Okay, 1a and 1b similar, that is when n is equal to 2, I am getting 2 a's and b's are 4 that are not matching. Okay, again 3 a's and 9 b's. So we cannot getting a pattern. Whenever we are not able to get a pattern, we can say that that is not a regular language, and also we are not able to check whether for how many a's we have to insert for particular b. For comparing b, we are not getting how many a's we have to insert. In previous example, we have seen that a raised to power n, b raised to power 2n was there. So we are clear that for comparing these b's, we need to push for one occurrence of a, we need to push 2 a's. But in this situation, we are not able to clear it. So we are not able to design a PDA for this. Okay, that is not a deterministic PDA, not a non-deterministic PDA. So we can say that this is not a regular language, and this is also not a CFL language. Whenever the language is not CFL, that means that is also not a deterministic context free language. Okay. Next is a raised to power n, b raised to power 2 raised to power 2, 2 raised to power n. This is 2 raised to power n. In this situation also, we are not able to get a unique solution, means we are not able to find a pattern. So initially, when n is equal to 1, we will get a b b as a string. When n is equal to 2, we will get a, then b b b b 4. When n is equal to 3, we will get triple a and 2 to the power 3, that is 8. So 8 number of b's, 3 3 6 7 8. Okay, and we will get such type of strings in the languages. Here 1a 2b, okay, double. 2a 4b's, that is also double, fine. When 3a's occurred, we need 6b's only, but we are getting 8b's. So we are not able to find out for a single occurrence of a how many a's we have to push into the stack. So this is not a finite language, and we are not able to find a pattern. So this is not a regular language, and we also say that designing a deterministic PDA or non-deterministic PDA is not possible for such language. But for this language, then we can say that this is not a context-free language. And whenever the language is not context-free language, then that is definitely not a deterministic context-free language. Again, so this is the language WW reversal, where W belongs to the A comma B whole star. So we have already seen this example. Solving by using, or we can say that designing a deterministic PDA for this language is not possible, because we are not able to get the center. We have to always check two ways, whether the center came or not center came. So by solving that example, by solving that way, we have seen that designing a non-deterministic PDA for this language is possible, but designing a deterministic PDA is not possible. So we can say that this is a regular language. So this is not a regular language, because we cannot solve by using finite automata, and this is not a DCFL. And when language is not DCFL, it can be CFL. So we have checked that by we can say that by using NPDA, we can accept such type of languages or such language. So this is a CFL language. Okay. So next example we will see, that is the language WW. W is the string which formed over a comma b. So if you will take W as suppose a, then the another W becomes also a. So we have identified, suppose anyhow we have identified, whenever we will push a, okay, and this a, the stack contains like this, z naught top of the stack, a, and whenever I will get this W is over, again I will use this W. This a is compared with this a and popped, and this a is compared with this a popped, and finally we are getting epsilon, and epsilon compared with z naught. So we will going to accept this, but the problem is that suppose we will get a string like this. Just a second. W. Sorry for that. Okay. So whenever we will get string like a b b, this is the W. Okay. So what we will do? This is my stack, and top of the stack is z naught, and I have pushed this a, b, and b into the stack. Now my top pointer is here. Again, suppose W is over, and again I have got this W, and I have to start popping. This is the epsilon. Now see, top of the stack is B and input starting from A. So I'm not able to compare these things. So we can say that whenever input is different and top of the stack is different, we are not able to pop. Okay, so from this example we can observe that by using this string we can observe that designing a, whether it is a deterministic PDA or non-deterministic PDA, is not possible for this language. Okay, so we can say that this is definitely not a regular language and not a context-free language. And when this is not a context-free language, means we can say that that is also not a deterministic context-free language. Okay, so next example is a raised to power n, b raised to power n, c raised to power m when n is greater than or equal to m. So here we are comparing, here a raised to power n is there and b raised to power n is there, and when we want to compare these, whether these whatever number of n, whatever number of a's are present in the language, that number of b's should be present in the string, that particular string. Okay, so what we will do for this, for comparing that, we need to push these a's into the stack, and by using these b's we can pop that a's from the stack, because we need to compare whether a's are equal to b's, and after that we will check n is greater than m. n should always be greater than m, ये होना चाहिए. But we can observe that, okay, I will take a stack and top of the stack is z0, and suppose the language becomes a, triple a is there, then definitely there should be triple b and c. Okay, cc is there. So these number of a's are pushed, and whenever b started occurring, I will pop that number of a's. So now you will ask why you are popping that a's, sorry, a's from the stack, because we want to check n is greater than m. But we should also remember that we want the string, okay, we have to accept the strings which are present in the language. So suppose if I will get a string like this, a triple a triple double b and this is cc, so this string will not be present in the language, because whatever number of a's are there, that number of b's should be there. But if I am not doing that, sorry, we can say that for occurrence of b, if I am not popping a, then we are not able to identify whether a's are equal to b's or not. Okay, so that's why I am popping for each b occurrence, whether I am left with z0, then only I can say that a's and b's are equal. Okay, and finally I am left with c only. Okay, now we can see that we cannot able to compare whether n was greater than m or not, because we are only left with z0 and c occurred, and we are not able to check, because the stack is containing nothing is there except that z0. So we can say that designing a PDA or non-deterministic PDA for this language is not possible. So this language is not a regular language, because it needs a more than one PDA or more than one stack, and similarly we can say that this is not a CFL, because designing a non-deterministic PDA is also not possible for particular language. Now this is the language, a raised to power n, b raised to power n, c raised to power n, d raised to power n when n is greater than or n is less than or equal to 10 raised to power 20. So here the n is bounded, or we can say that n is finite, and whenever n is finite, then I have already said that whenever language is finite, that is a regular language, because for this language we can able to form a DFA, that is finite automata. So if the language is regular, then it is a accepted by DCFL also and CFL also. Means the language becomes DCFL and CFL also. Okay, let's see more examples. So the question is, so the question is a raised to power n, b raised to power 2n, c raised to power 3n, where n is greater than or equal to 1. So let's try to identify the strings. So basically when a is equal to 1, if I will write a is equal, that is n is equal to 1, the string becomes a, b, b and triple c. Okay, when n is equal to 2, then a double 2, b is equal to 4 b's and c is equal to 6 c's. 4, 5, 6. So we will get such type of strings. So definitely this is not a regular language, because we are not able to design a finite automata, because for comparison we need a memory. Now for this we can say that, okay, one occurrence of A we are getting 2 occurrences of B and 3 occurrences of C. Similarly, whenever A is equal to 2, we are getting 4 B's and 6 C's. So one logic behind this, we can say that for single occurrence of A, we can push 5 A's and then we will compare. But that is wrong. How? If for one occurrence of A, if we will push 5 A's in the stack, then stack will look like this. So Z naught A, 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 and this A, and top becomes here. So definitely we will compare these two B's and we will pop this A, okay. Now when C occurred, again we will pop one by one A's for that, and finally we can say that this string is accepted by using this type of finite automata. Even such strings also accepted by using this logic. But in previous class we have discussed, we want a finite automata or PDA or machine, we can say that, in such a way that that machine should be a language accept, not a string accept. When we are saying that language accept, means it will accept all the strings in the languages, but it will also reject, it should have to reject all other strings which are not present in the language. But suppose I will take one string like a, b and 4 times c, this string will not be generated by using this language, but this string, if you will compare, or if you will try to solve by using our logic is that whenever a comes we have to push 5 a's in the stack, but this string will be working here, because how, for this a I have pushed 5 a's, and whenever b started occurring I have popped this a. Okay, again for this c I have popped this a, for this c I have popped this a, for this c I have popped this a, and for this c I have popped this a. I am left with z naught, and here finally epsilon is there, so I can say that, okay, this string is accepted by my PDA, but this should not be happen. This string is not belong to this particular language. Okay, so we are not able to design a correct PDA for this language, so we can say that this is not a context free language also. This is not a context free. Understood? Similarly, one more example is this: a comma b is any string possible over the 0 comma 1, means a is either 0 1 and b is, okay, 0 0 0 0. That should be there, because a and b are independent. This star means that this star nothing means a raised to power n, b raised to power n, nothing like that. Okay, a and b are independent, and only c is like, c is the substring. Okay, so this is A and this is B, then C is the substring. Okay, so we have seen that some examples, or you have already gone through such type of examples in finite automata. Okay, so for this language we can able to design a finite automata. Like suppose roughly if I will draw, this is q naught, and here I will get anything that is 0 comma 1, and after that c is compulsory. C is compulsory, so because the string contains c, and minimum length string possible over this language is c only. Sorry, this is c, then one length string, so it will be 0 c is also possible, or c0 c1, this is also possible. So I will move to the q1 state, and that q1 state is final, and in that final state also I am accepting anything that is 0 comma 1. Only thing I need is string contains c. So this is a regular language, and when the language is regular, it is accepted by PDA also. So this is DCFL and CFL also. Okay, we will see some more languages. So first language is like x and x raised power r, that is reversal of the x is a string, and x reversal, that is the x reversal of that x only. Okay, and x is anything between, that is formed over a comma b, and length of x is fixed, that is l, and l is anything. Okay, but this l indicates it's a finite. Okay, l is a finite, and whenever the language is finite, we can directly say that that is a regular language, because forming finite automata for a finite language is possible. So this is regular language. So similarly we can say that this is the TCFL also and CFL also. Okay, next example, WW reversal, where W belongs to a comma b whole closure. So we have already gone through such type of example. Even WW is not, or so we can say that for WW itself we are not able to form a push down automata. So here the language is like WWW reversal, so this cannot be possible. Or we can say that designing a PDA, whether it is not deterministic or non-deterministic, is not possible. So I can say that this is not a regular language, because we need memory, and with one stack we are not able to design such design PDA for such languages. So this is not a DCFL and not a CFL also. Next, a to the power n, b to the power 3, 3 to the power n. Okay, so this is the language, and we have already seen that 2 to the power n itself is not a possible to form a, or to design a PDA for that language. So we can say that for such type of languages designing a PDA is not possible. So this is not a regular language and not CFL language. And when it is not a CFL language, definitely it is not a DCFL language. Let's see more. So next language is a raised power m, b raised power n, where m is not equal to n. So whenever we have to check m is not equal to n, we need an memory. Okay, so we need a stack. When what we will do, we will push a's into the stack, and whenever we will left like this, suppose b is the input and we are left with z naught after popping a's, then we can say that okay, m is not equal to n. And in another case, whenever we are left with epsilon and top of the stack is a, we are getting, then we can say that m is not equal to n. And so checking, or so we can say that designing deterministic PDA for such type of languages, or for such language, is possible. So definitely this is not a regular language, but it can be a DCFL, and whenever the language is DCFL, it is a CFL also. Okay. Similarly, we will check the next one, that is a raised power m b raised power n, where m is equal to 2n plus 1 is there. So in this situation, m is 2n plus 1, and we have already seen such type of example when n yeah, a raised power n b raised power 2n, and a raised power n b raised power 2n plus 1, and so forming a deterministic PDA is possible for this language. So we can say that this is not a regular language, but it is a DCFL language, because we can design a deterministic PDA for language. And similarly, if this is a deterministic context free language, then it is also a context free language. Okay. Next is a raised to I b raised power j, and where I is not equal to 2j plus 1, and this is also will be also checked by, because we need to just equate that I is not equal to 2j plus 1. So for single a, what we will do, we will push 2 a's also, and if we will end up with a situation like this, a and this is z naught. Okay, so again we will compare like this. Okay, a, I am left with a, and now after, sorry, I'm left with b, and top of the stack is z naught, so we can say that I is not equal to 2j plus 1, like that. Okay, so comparison is possible, and we are able to design a DCFL for this one. So this is a CFL also. Again, next one is a raised to power n square. So in this language, if we will put 1, n is equal to 1, then we will get single a. Similarly, n is equal to 2, we will get 4 times a. Similarly, n is equal to 3, if we will put, then we will get 1 2 3 4, 3 to power 3 square is 9, so 9 is 6 7 8 9. Okay, so we will get such type of strings present in the languages, but one thing is that we are not able to form a deterministic PDA or non-deterministic PDA for this. Not even regular, finite automata can not be designed for such languages. So if we will look this one, it will look like a simple, okay, why we should not do like this, q naught is there, and okay, we will accept here a, that's it, and this is the final state. So if we will closely check this, then epsilon is also accepted by this finite automata. Similarly, double a is also accepted by this finite automata, but this should not be happen, because that is not present in the language, that string not present in the language. So we can say that this is not in AP. In AP means arithmetic progression, means there is no pattern, we are not able to identify the pattern. So if we are not able to identify for the pattern, so definitely this is not a regular language, and also we can say that designing a PDA is also not a possible. So we can say that this is a not a contextual language. Okay, let's see more examples. So the next language is a raised to power 2 raised to power n, when n is greater than or equal to 1, greater than or equal to 1. So if we will write the strings present in the language, we will not get any pattern between the strings. Okay, so we can say that this language is not in AP. So if language is not in AP, that is not a regular language, even we are not able to design a PDA for that. So this is not a contextual language, we can say that. Then a to the power m is there. When a to the power m is there, m is a prime number, so we can say that uh, m is a prime, so we will not get any pattern in that. So this is also not a context free language. Okay, a raised to power n factorial, where n is greater than or equal to 1, in this also we will not get any pattern, so we are not able to design a EDA for this one, so this is also not a context free language. And finally, a raised to power k is there and k is even is there. So whenever k is even means a even number starts from 0, suppose. So language contain the strings like epsilon, okay, then double a, then 4 times a, because I am getting even numbers, so 6 times a, okay, then again 8 times a, okay, k is even. So I am getting a pattern, and whenever I am getting a pattern, I am able to design a finite automata for this one, because we will put that pattern in the loop, and designing finite automata is possible for this language. So we can say that this is a regular language, and whenever the language is regular, that is DCFL also and CFL also. Okay. So here are the some languages. For this language, I'm not going to solve whether it is a context free language or regular language or not. Okay. So I giving you as a homework for these languages as a homework. Kindly check these languages whether it is a regular language or context free language or deterministic context free language. Okay. So these are 12, 13, 14, 15, 16, and also we are having 17, 18, 19. Okay. So in frame I will put that in one frame. Okay, just a second. So okay, so these are the languages. Kindly solve these languages and check whether these are regular languages or context free languages or deterministic context free languages. And after solving these languages, kindly put the solution, or like this 12 answer is like, okay, this is context free language, deterministic context free language, in the comment box, and check whether your answer is correct or not. Finally, the solution of these I will put into the Telegram group, but I request you all, kindly put the solution in the comment box. Okay. So thank you so much. We will see in the next class. Thank you so much.